Hi folks, I'm Mr. Pinola, and I hope you enjoyed seeing those couple of fireworks with me. Do you know why you always saw the firework explode before you heard the sound that it made? That's because light travels faster than sound. Sound, as we learned about last unit, is a mechanical wave. And in air, sound travels at roughly 340 meters per second. That's around 720 miles per hour. Fast, but not quite as fast as light. Light is an electromagnetic wave, or an EM wave, like we talked about in the last video. And light travels much, much, much faster than sound does, as evidenced by the fireworks, or as shown by the fact that you always see lightning before you hear the thunder. Today, we're going to look more at the speed of light, or really the speed of any kind of electromagnetic wave. So, how fast does light or any electromagnetic wave really travel? Well, this was a question that stumped scientists for many, many years until a man named Albert Michelson did an experiment outdoors, which became really the most accepted way to measure the speed of light, or really the first of his kind. Michelson went to the top of a mountain nearby where he lived. I'll draw a little bit of a sketch of what that looked like. He went to the top of Mount Wilson. And there was another mountain nearby that was called Mount San Antonio. And when I say nearby, this was a good number of miles away. Now, even though the mountains were a decent distance away, you could see the top of Mount San Antonio, the second mountain, from the top of Mount Wilson, the first mountain. And Michelson knew that if he was going to find the speed of light, he had to measure it over a big distance. So he gave the light a long time to travel out and then come back. And so he went to the top of Mount Wilson, and he brought with him two things. The first thing was a rotating mirror. The mirror looked kind of like an octagon. It's the shape that a traffic light would look like. And it was rotating so the mirror could spin around and around and around. He also brought with him a laser beam. And so he shined the laser beam at one part of the mirror. And when it struck a certain angle on the mirror, the light traveled all the way from Mount Wilson to Mount San Antonio. And it traveled in a straight line through the air in between the mountains. When it got to Mount San Antonio, Michelson had already set up on that mountain a mirror, just a flat, plain mirror that would reflect the light all the way back to where he was on Mount Wilson. And so the light did exactly that. He knew where the light would strike. And the laser beam traveled in a straight line right back to where it came from. Well, not exactly right back to where it came from. And that's because it would strike the rotating mirror in a slightly different place. And it would then be reflected off of the rotating mirror. Now, the physics behind this can get pretty complicated, but what you need to know is this. Michelson was able to use this big distance through which the light traveled, and also the knowledge of how far the mirror would rotate by the time the light returned to measure the speed of the light. And if he knew the speed of the light, then he would know the speed of any electromagnetic wave, like some of the ones we learned about last time. So, Michelson then said that he calculated the speed of light in air, because he knew that there was a whole lot of air in between the mountains. That was the medium through which the light traveled. And according to his data, he found the speed of light was a lot more than the speed of sound. Remember, the speed of sound was about 340 meters per second. The speed of light was 299,976,000 meters per second. In miles per hour, that's about 186 million miles per hour. That is tremendously fast. We can't even comprehend how fast that possibly is. Now, Michelson also realized that light is an electromagnetic wave, which means that it doesn't need a medium to travel through. So if there was a vacuum or a region with no air in between the mountains, the light would travel even slightly faster because there wouldn't be air in the way of the electromagnetic wave. And so he took his number that he found for the speed of light in air, and he said, I can also know what the speed of light in a vacuum is. And so all he did for that is he took an approximation. He took his speed of light in air and he rounded up because he knew the speed was slightly, but not much, greater in a vacuum. So he rounded up to 300 million meters per second and say that is the speed of light or the speed of any electromagnetic wave in a vacuum. If you wanted to write it out, you could say that it was 300 million meters per second, because that's a lot of zeros. It's really hard to remember exactly how many zeros there are. So some places you'll see it written as 300 million meters per second. But I know what you might be thinking. There is a more scientific way to do that. In fact, Michelson also took this number and he wrote it using scientific notation, because scientists use scientific notation so they don't have to write all those pesky zeros at the end. And so the speed of light in scientific notation is 3 times 10 to the 8th meters per second. So whether you choose to express the speed of light or the speed of any electromagnetic wave as the exact measurement that Michelson got, or as his rounded measurement, or in terms of words, or in terms of scientific notation, it's pretty clear the speed of light is, or really the speed of any electromagnetic wave, is incredibly fast. Thanks to Albert Michelson's work, we now had a measurement or a number for the speed of light or any electromagnetic wave in air and also in a vacuum because it was a really close measurement. However, Michelson extended this. He said that's not only the speed of light in air, it's also the speed of any electromagnetic wave, such as ones that we've discussed before. So radio waves, meaning the waves that your car uses to collect a radio signal, microwaves, other types of waves called infrared rays. We'll learn more about these types soon, but let me list some more of them out. Visible light, like Michelson's laser beam. Ultraviolet, or as you might know better, UV rays. X-rays, and gamma rays. All these common types of electromagnetic waves all had the same speed. And Albert Michelson found that the speed that all of these kinds of waves had, because they were all electromagnetic waves, was 3 times 10 to the 8th meters per second. Or in other words, 300 million meters per second. Notice that I didn't include sound on this list. Remember, sound is a mechanical wave. It's not an electromagnetic wave. And so sound would be on its own list and would have a speed in air, because sound can't even travel through a vacuum, of only 340 meters per second, which is still fast. but it's not nearly as fast as 300 million meters per second. But let's only focus on electromagnetic waves. There's one last big observation that we can make from here. Do you remember when we first learned about waves, we studied the wave equation? That was the equation that told us that the speed of the wave, or the velocity of the wave, was equal to the frequency, measured in hertz, multiplied by lambda, which represents the wavelength, measured in meters. Well, Albert Michelson realized that if we knew that a wave was one of these electromagnetic varieties, we would automatically know its speed, assuming that it was traveling through air or a vacuum. And if we automatically knew the speed, and we knew either the frequency or the wavelength, we could find the other one. And so if we wanted to find the frequency of an electromagnetic wave, all we would have to do is divide both sides by the wavelength, and the speed of the light divided by the wavelength would equal the frequency. We could do the same thing if we wanted to find the wavelength by dividing both sides by frequency. So not only do we now know what the speed of light is, or really the speed of any electromagnetic wave, but we can also now use that speed of electromagnetic waves to help us when doing calculations using our three-step method.